So in the last lecture, we talked about Taylor polynomials and how we could use these Taylor polynomials to approximate non-polynomial functions near a given point. And we saw that adding more and more terms to a Taylor polynomial improves the approximation. So you wonder what happens if you just continue adding terms to a Taylor polynomial. I mean, can we model the whole function? With a Taylor polynomial if we just keep adding more and more terms? How far out from the point we're modeling around is our approximation valid, right? So that's where we get into Taylor series. And basically the Taylor series is the same thing. It's just that we have a polynomial that just goes on forever, all right? So that's what we're calling a Taylor series. So we have a Taylor series formula for, about x equals 0, which looks just like what I presented in the last lecture. And we also have a Taylor series polynomial for a function around a different point other than 0, x equals a, right? And the only thing different is that we're expressing our polynomial in terms of x minus a instead of just x. Okay, so there's not a whole lot new here, except we're getting into the idea of having this infinite series, infinite sum of these polynomial terms. So let's just find the Taylor series for f of x equals e to the x around x equals 0. Okay, we actually did this already, right? What we need the value of the function at 0, so f of 0 equals 1, right? That's just because f of x is e to the x, e to the 0 is 1. And e to the x is nice because the derivatives are just all e to the x, right? So the first derivative is e to the x, the second derivative is the derivative of the derivative, which is e to the x, and the third derivative is e to the x, right? Every time we take the derivative, it's still just e to the x. So I guess I'll write it down here. So if we evaluate those derivatives at 0, we're just always going to get 1. Right? E to the 0 is 1. So every one of these derivatives evaluated at 0 is just 1. Okay? And we could just keep going on and on. Because we're doing a Taylor series now, so we're going to have a polynomial that goes on and on. But of course, we can't write all of that out. So we just write ... Okay, so all right. So our Taylor series for e to the x is just going to be, okay, so f of 0 is 1 plus the derivative at 0, which is 1 times x, plus, okay, then we have the second derivative, which is 1 over 2 factorial times x squared, right? I'm just plugging numbers into the Taylor series formula right up above here. And the third derivative at 0 is 1 over 3 factorial times x cubed, and we could go on and on from there, right? So right? You can see the pattern, and it just keeps going. So that's nothing new. I mean, we pretty much already did that in the last lecture. So another question we might ask, what is the general term for the Taylor series of e to the x about x equals 0? So what do we mean, general term? All we're asking there is, can we write an expression for the kth term in terms of this integer k, right? So we'd want to, if we want the first term, put in 1 and we'd want to get the first term. All right, so now there's a little bit of so k is an integer, right? K is an integer, but sometimes it's easier to start with counting at 0 rather than 1. So a natural way to write the first term is that we have 1 over k factorial. Okay, now one thing you have to remember is that 0 factorial is equal to 1, as well as 1 factorial is equal to 1. Okay, So if we put in 1 or 0, we're going to get 1 for this term. All right, and then we have x to the k. Now, that works if we start with k equals 0. So this would be the general term for k equals 0, comma 1, comma 2, comma so on, right? So if we want the 0th term, which is basically this what we might call the first term, but the first one in the list, if we put in 0, we get 1 over 0 factorial, which is 1, and then x to the 0 is also 1, so we get 1. Okay, if we put in k equals 1, right, we get 1 over 1 factorial, which is 1, and then x to the 1, which is x. Okay, so that gives us we would call that the first term, and then we call this the 0th term, and we call this the first term. Okay, so sometimes the term number, it depends on where you start, right? Now we could also write this if we want to write this for k equals 1, comma 2, comma 3. We can do that. It's just not as pretty. It's a little, but it's not that much. It's not that bad. So basically, we would have 1 over k minus 1 factorial. Now don't forget the parentheses, because if you leave out the parentheses, it looks like k minus 1 factorial, where the factorial is just applied to the 1. If you want a factorial applied to the whole thing, you have to put parentheses around it. Okay, and then we'd have x to the k minus 1. And that way, when we put in 1, we get 1 over 0 factorial times x to the 0, which is the 1, right, the first term. And then if we want the second term to be the second term, k equals 2, we put in k equals 2, we get 1 over 1 factorial, and then x to the 2 minus 1, which is just x, right? So so there's not we could write this either way, depending on how we want to define k. So oftentimes, though, you'll see it this way just because it's simpler to start at 0. So and also we call k is also called the index. So you might see that term used in some of the homework problems, but so that's what that means. K is the index. Okay, so now we've done e to the x. Let's try another one. Let's try a different function to model. Okay, so now let's take a look at cosine of x. And we want to, again, come up with the Taylor series about x equals 0 for cosine of x. So, well, let's see. So f of 0, if we put in 0 to cosine x, we get 1, right? So now we can just look at the derivatives here. Now, the first derivative of cosine of x is equal to the negative sine of x. Okay. And the second derivative, the derivative of the derivative, is going to be minus cosine of x. Okay, so we just keep taking the derivatives of the previous derivatives. We just got derivative of minus cosine of x is going to be minus the minus sine of x, so we get sine of x. And the fourth derivative, let's do the fourth derivative at x, is going to be derivative of sine of x versus cosine of x. And you can see we're back to where we started. So now if we want the fifth derivative, it's just going to be the same as the first derivative. So this is also the fifth derivative, right, of x. And so, and then, just cycles around. So this is also the sixth derivative of x. And the third derivative is also the seventh derivative of x. And so on, right? So this is also the eighth derivative of x. Okay, so you can see there's a cycle going on here. All right, so now let's compute the values at 0. So f prime at 0, we put in f of, if we put in 0 to negative sine of x, sine of 0 is 0, right? So that's going to be 0, which means that also the fifth derivative is 0. All right, so the second derivative at 0 is, okay, we put in 0, cosine of 0 is 1, but it's negative of that, so the value of the second derivative at 0 is -1. And then the third derivative at 0, again, sine of 0 is 0, so we get 0. And then the fourth derivative, of x is we just put in 0 into cosine x and we get +1. Okay, and then those would just keep cycling, right? So now that we've computed the first, second, third, and fourth derivatives, that means we also have the fifth, sixth, seventh, and eighth derivatives. So let's write this Taylor series. So we have f of x is equal to, and we're going to start with the value of the function at 0, which is 1. Okay, now the second term is 0, right? So I'm not even going to bother to write that. I'm going to go straight to the second, well, the third term, right, which is based on the second derivative. So I'm going to get -1 over 2 factorial times x squared. And again, we can skip the third derivative term, and we're going to go to the fourth derivative term, which is going to be plus 1/4, right, because its derivative is 1 over 4 factorial, 1 over 4 factorial x to the fourth. Okay, and then we can skip the seventh derivative, or sorry, we're on the fifth. Okay, right, the fifth derivative is the same as the first derivative, so it's 0. We can skip that, and so we're just ending up with the even derivatives. So we get 1 over 6 factorial x to the sixth, right, because the second derivative was -1, so that also means that the sixth derivative is also -1. All right, and then we can skip the seventh derivative and go to the eighth derivative, which is going to be the same as the fourth derivative, which is 1, and so we have 1 over 8 factorial x to the eighth. So you see, we just have even terms, and we have even factorials, and then the signs alternate, right? Positive, negative, positive, negative, positive, negative. So there's a nice pattern there. So what is the general term for the Taylor series for cosine of x? Well, first thing, we have this alternating sign, right? So if we take -1 to the kth power, right? Whenever k is even, we're going to get a positive number, and whenever k is odd, we get a negative number. So a good way to get that alternating sign is just to take -1 to some power, right? So that alternates even, odd, even, odd, even, odd, even, odd. So now I want this first term to be positive. So I'm actually going to, I'm going to write this over here. I'm going to actually have k start with 0, because then -1 to the 0 power will be a positive 1. And then when I put in 1, I'll get the -1. Okay, so which I want the negative on the second term, right? Which is going to be actually the first term, right? So, all right, so that gives us the alternating sign. And then I want even factorials. Now, the way to get an even number is just to multiply it by 2. So I'm going to take 2k, right? I'm going to multiply by 2. That way I'll just get even numbers. I'll get 2, 4, 6, 8. If I start with 0, I'll start with 0, 2, 4, 6, 8. Okay, and so I want to make that factorial. All right, so you see if I put in 0, I get 0 factorial, which is 1. That matches up. When k is 1, I get 2 factorial. When k is 2, I get 4 factorial. So I'm just going to get the even factorials. And then I want powers of x. And I just want the even powers of x. All right? And we can consider this to be like 1 times x to the 0, right? Because x to the 0 is just 1. So I'm just going to make this, and I just want the even ones, so I'm going to do x to the 2k. So that'll give me x to the 0, x to the 2, x to the 4, and 6, and 8, and so on. If I use this, if I start my k values at 0. Okay, so k is an integer starting at 0. 0, 1, 2. Okay, so that's an expression for the general term. It's not the only one, but there's all kinds of there are different ways that you could write that, or you could write it starting at 1, if you wanted to. But this seems to be, I think this is probably the simplest way to write it. All right, so this is one I want you to give a go on. So this is sine of x, okay? So, but it's the same process. So I'm going to have you pause the video and give this a try, and then you can come back and check. All right, so I've completed this problem, and hopefully it matches what you got. So again, you get this cycle of derivatives, right? You take the derivative of sine, you get cosine. Derivative of that is a negative sine. Derivative of that is the negative cosine. And then the fourth derivative is sine again. And so we're just going to get this cycle of derivatives. Okay, and you also can see that when we evaluate the derivatives at 0, all of these even derivatives are 0, right? So we end up with just the odd terms in the Taylor series. Okay, so now writing the general term can sometimes be tricky. So I decided to just go through this with you again. So again, we have this alternating sign: positive, negative, positive, negative, positive, negative. So if I you know, I know that there's got to be a -1 to some power involved. Okay, so I'm just gonna do -1 to the k, where k is equal to 0, 1, and 2, and so on. Okay, because that'll give me the alternating sign that I want, right? When k is 0, I'll get the +1. When k is 1, I'll get the negative, and so on. So it'll alternate the way I want it to. Now, in this case, we've got these factorials in the denominators, but they're the odd factorials rather than the even factorials. But an odd number is always an even number plus 1. So we can always get an even number by multiplying by 2. So the trick here is to write an odd number as 2k plus 1, right? Factorial. And then sometimes you just have to try things and then check it, because you could also get it by doing 2k minus 1. But we want to then check to make sure that, okay, if we define k as being 0, 1, 2, 3, so on, does that give us what we want? So if I put in 0 for k, right, I get 0 plus 1 factorial. So that's 1 factorial, which is 1, right? So I'll end up with +1 over 1 factorial, which is just 1, and then and so that gives me that coefficient on the x term that I want. And if I put in if I put in 1, right? Now I put in 0 first. Now I'm going to put in 1, and that will give me the 3 factorial in the denominator that I want. Okay, so that seems to check out. So the 2k plus 1 seems to work. And then we want then powers of x, right? And basically the powers of x match the number in the factorial, right? If we have 3 factorial in the denominator here, then we have x to the third. So I'm just going to make the power of x also be 2k plus 1, and then that should work out. So there's an expression for the general term. So those are, they're a little tricky sometimes, and so oftentimes what I'll do is just try something and then test it for 0, 1, 2, 3, make sure I'm getting what I'm expecting to get. All right, so now let's talk about, there's one last thing I want to talk about here, and it's just the convergence of a Taylor series. Now, we're going to talk more about Taylor series at the end of this course. There's a whole section on series and sequences and convergence tests. And so even the term convergence, you haven't really learned the technical definition of the word convergence yet. But the idea is that if you add more and more and more and more terms to a Taylor series, are you going, how closely can you get to the actual function you're trying to model, and what range of values will it converge? will the function you're modeling or how well will the Taylor series represent the function you're trying to model? So, so this last example that I'm going to go through is just kind of introducing that idea of convergence. And so, first of all, we're going to look at the Taylor series for the natural log of x. around x equals 1. Okay, now we did this in the last lecture too, so, but let's go through it again. So we know that f of 1 is equal to 0, right? So that's going to be our first term in our Taylor series. And then we can look at the derivatives. So f prime of x is just 1 over x, which I'm going to write as x to the minus 1. Oops, let me make myself a little more room here. Okay, so we can look at the second derivative, right? And I'll get minus x to the minus 2. I can look at the third derivative, and I'll get 2x to the minus 3. And I'll look at the fourth derivative. And that's going to be minus 6x to the minus 4. Okay, now we don't have a nice pattern going on here. You know, but, well, we kind of do have a pattern. You know, the exponents on x are being reduced by 1 every time. So we get exponents that go -1, -2, -3, -4. And then you can see that the coefficients are just going to be factorials, right? So like the next coefficient is going to be basically 1 times 2 times 3 times 4, right? If we took the fifth derivative, right? So so we get these coefficients that are factorials lagging behind the derivative by 1, right? Because this is basically 3 factorial. But it's negative, right? And this was 2 factorial, but it's positive. So we also get this alternating signs. So we sort of have a pattern here. But now we'll evaluate the derivatives at the point we're trying to model, which is 1. So f prime of 1 is 1. F double prime of 1 is going to be -1. The third derivative at 1 is going to be 2. And the fourth derivative at 1 is going to be -6, right? So it's really easy to put in 1 because 1 to any power is just 1. All right, so now we can model this function, f of x. Okay, so we have f of 0, which is just 0, or sorry, f at 1, which is 0, right? And then we're modeling it around 1, so all of our powers of, instead of powers of x, we're going to have powers of x minus 1. Okay, and then we have 1 over 2 factorial times x minus 1 squared. All right, this is just using the formula. And then we're up to the third derivative now. So third derivative is 2, and that's over 3 factorial. X minus 1 cubed minus, let's see, we have 6 over 4 factorial. It's minus 6 over 4 factorial times x minus 1 to the 4th power, and so on. Okay, so I can simplify that a little bit because these factorials will have some factors that cancel here. So we have, I can just leave off the first term. So we get x minus 1, oops, x minus 1, I want a minus sign, x minus 1 minus 1/2 x minus 1 squared plus, now this is 3 times 2 times 1. So this is just going to be 1/3 x minus 1 cubed. And this is 4 times 3 times 2 times 1. So you can see we have these factorials in the numerator just lagging behind the factorials in the denominator, right? So here we're going to end up with 1/4 x minus 1 to the 4th, and so on. Okay. Now, there's, you may have learned at some point sigma notation. So I just want to throw this in here. It's not necessary at this point, but we can represent a sum by using this sigma notation. And so we could say that for n equals 1 up to infinity, so our Taylor series, and then we can write the general term. So that's really the important thing about the general term, is that then we can write it in a more compact form. So, okay, so we have these alternating signs. All right, so we got -1 to some power, but I want the first term to be positive, and if I use n equal, if I start at n equal 1, then I probably want to advance it by 1, right? Because I want an even power of -1 in order to get a positive 1 on the first term when n equals 1, right? And then we could actually write this as 1 over 1. So we have 1 over 1, 1 over 2, 1 over 3, 1 over 4. So basically we have n, right? We have the fractions. We have what -1 to the n plus 1 over n, and then we have powers of x minus 1. Okay, and we're starting with x minus 1 to the first power, and then second, third, fourth, and so on. So it's to the n. Okay, so we could write this Taylor series in this more compact form using the sigma notation, right? So essentially what you're doing is kind of like a for loop in programming. You know, you're cycling through, and n equals 1, you write that term, plus let n equal 2 and write that term, plus let n equal 3 and write that term, and so on. Okay, you'll get the same thing. Okay, so but in any case, this is the general term. Okay, so the other part of this problem is just asking you to investigate the convergence of this ln of x by graphing the first several partial sums, right? So we could look at the linear term. We could look at the Taylor polynomial, the first order Taylor polynomial, and then we could look at the second order Taylor polynomial, and the third and the fourth, and so on. Now this was done in your book, so I just copied this nice little graph. Now you can do this on your graphing calculator, or you can use a graphing program like Desmos. Desmos, I don't know if you've ever used that. It's pretty slick. You just type in equations and it'll graph it really nicely for you. And then you can look at, okay, what's happening around the point we're trying to model. So you can see it's modeling pretty well through here. Let me use a highlighter here. Through here, it seems to be modeling pretty well, right? And but outside some region, it's not doing it, right? It might, over here it kind of looks like it's getting closer and closer, but over here it looks like it's flip-flopping. All the even polynomials, right? They're all looks like they're going to -infinity, and all of the odd polynomials are going to +infinity. So what we could do is we could just say that the series, this Taylor series, appears to converge. Now we don't have a way of proving this yet. So for x values between, and now they have it marked between 0 and 2, right? So between 0 and 2, this Taylor series looks like it's converging. It's approximating the function better and better. Outside of that, though, it doesn't seem to be doing that well. Okay, so the point is that you can't necessarily model the whole function with a polynomial that's modeled around a certain point, but it will. But oftentimes there's what we call a radius of convergence. All right, so we model it around this polynomial around x equal 1, and we can see that on either side of that point, it's converging within a certain radius, and beyond that, it doesn't work so well. So we're just introducing the concept here, and we're going to revisit this later. So, well, there's some, again, discussion questions for you to work on, and we'll see you later.